In a previous video, we learned how to test for a population proportion. We had a guess for what percentage of the population had a certain characteristic. We performed a sample, we got sample data, we got a p-hat value, and we used that to decide whether the null hypothesis was wrong or not, and we did all that before. But now what we're doing is we have two different population proportions, maybe the percentage of men that do something, the percentage of women that do something, and we're trying to compare these two population proportions. Maybe we're trying to show that one of them is bigger than the other one. Maybe we're trying to show that one of them is smaller than the other one. Maybe we're trying to show that they're just different from each other. So these are the setups here. Now, it's going to be a little bit trickier because when you have two different things going on, you have to make sure everything is good to go. But for the hypotheses, those are pretty straightforward. Your H0 is that your P1 is going to equal to P2. So your default assumption is always going to be that your two proportions are equal. And then you can go ahead and make your alternative hypothesis being where, say, your first proportion is smaller than your second proportion. Or you can say the first proportion is different than the second proportion. And we honestly don't even need to have a third variation. Although if you want to, you can put it down. The reason why you don't need a third is because, let's say you are trying to show that P1 is bigger than P2. You could have just gone back to the first variation here and then switched the order of which one you put first. So it doesn't really matter which way you set it up here. Now, it turns out that as long as you are in certain nice conditions, we're going to be able to use the normal distribution to calculate our p-value for this problem. Now, of course, the question is going to be, what conditions do we need? And I'm not going to go through all the details in this video, but we saw before that you wanted things like n times p times 1 minus p to be at least 10. So now you need the sample for the first one times the p for the first one and 1 minus p for the first one. You want that to be at least 10. And you want the same thing for the second one. So basically you need this condition to be true for both of the proportions you're talking about, the sample proportions. I put greater than equal to 0, should be greater than equal to 10. And you also want to make sure that your sample sizes aren't too large. You want to make sure your samples are independent and randomly chosen. And, you know, there's all those typical conditions we'd want to have to make sure our samples are good. However, in this class at least, those are going to be true because otherwise we don't have a way to calculate our answer here. So once we understand that and we can use our normal distribution to get our answer here, we're going to do that in the TI-84 calculator. Before I get that, let's take a look at our example here and write down what we're trying to use. So it says, a new drug is being tested for side effects before going to market. An experiment was performed where individuals were randomly chosen to receive this new drug or a placebo and then asked if they developed nausea later. For the group that took the new drug, 120 out of 685 experienced nausea, while in the control group, 52 out of 635 experienced nausea. Does this data support the claim that the new drug causes nausea at a higher rate compared to taking a placebo using the alpha as 0.01 level of significance? So we have two things here. We have our first sample, N1. There were 685 total people, and the number who had nausea would be 120. So that means your P1 hat is 120 out of 685. And we can convert that to a decimal right now if we want to, or we can just type it in the calculator as a fraction. That way we don't have to try to round it right now. Our second sample, N2, is 635. Our second X2 is 52, which makes P2 hat 52 out of 635. Our null hypothesis is always going to be that they are equal to each other. And then what are we trying to do here? We're trying to say we want the drug, we want to test whether it causes nausea at a higher rate. So the P1 was the people that took the actual drug. So we're trying to test whether that rate is higher than the rate of people that took the placebo pill. So we set up the null hypothesis. We've summarized our data here. We know our alpha is 0.01. So now we're going to take all this information and go ahead and put it into our calculator here. So if I pull up the calculator, remember when we're doing hypothesis tests, we're generally going to hit the stat button, go over to tests. Now for this one, we are doing proportion, and there's two proportions, and we're using the z for the standard normal. That's exactly option number 6 here, 2 prop z test. So we go ahead and hit enter there. And then we have our data. Our x1 was 120. Our n1 was 685. Our x2 is 52. Our n2 was 635. We're trying to show that P1 is bigger than P2. Yep. So we go ahead and hit calculate there. Now, this one, I want to point out something that I've seen a lot of students have trouble with in the past. When they look where it says P equals, that's your p-value, and it says 2.44, they're like, wow, that's a really big number. But it's not, because if you look at the very far end over here, that's 2.446 e minus 7. So let me write that out over here, 2.44 e minus 7. So my p-value is 2.44 e minus 7. What does e minus 7 mean? It means you start with the number 2.44 and you move the decimal place to the left 7 places. That's why it's negative, it's to the left. So 1, 2, 3, 4, 5, 6, 7. So we're going to have the decimal point here now, and then all of these are zeros. So it's really this ridiculously small number here. Really, 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 really small number. So don't be confused when they have that weird calculator notation with the e minus number. It just means move the decimal place over that many times. And to be honest, when you're doing these problems, if you see the e minus number, you already know it's going to be a ridiculously small number, because otherwise they wouldn't have used that notation. So you can pretty be sure it's going to be, the p-value is going to be less than your alpha. All right, this p-value is much, much less than the alpha, which is 1%. Where, like, let's see, this is where the 1% would be. This would be 1/10 of a percent, 100th, 1000th, 10,000. This is like 1 or 2 100,000ths of a percent. Really, really, really tiny. Way too little to happen by chance. So what that means is that in this drug, the people who took the actual drug had a significantly, definitely a higher rate of getting nausea compared to the people that were taking the placebo. And that means that there is sufficient evidence. There's really sufficient evidence, if you want to be, more emphatic about it. There is sufficient evidence to say that the new drug does have nausea as a side effect. Now, this is not the exact thing that the drug manufacturers do. It's not the exact numbers and so on here. But this gives you a good idea of how it works. So they do these trials and they look at and see, what outcomes the different people might have. And, for example, let's say someone gets a headache. Is that really going to be a side effect, or did that person just get a headache? And so they needed this control group to compare it to. And they look at the rates that people might get nausea, people might get headaches, and so on. And they kind of test each one of these things, see what's going on. And then whenever you have something significant, hey, that means we're going to have to report that that is a possible side effect of this medicine. So this is at least the idea behind some of those medical trials and how they work when trying to figure out what the side effects are. They're not going to put down every single thing that every patient felt. Because again, that patient We're not going to put down that their foot was hurting, but maybe because they stepped on something and that's why their foot was hurting. So they have to do some sort of control here to indicate what is actually happening as a result of the medicine, or at least seemingly as a result of the medicine, compared to the control group. And this is the process for doing a two population proportion hypothesis test.